We're going to briefly introduce you to something called sigma notation. And sigma notation is this funny looking E here. In fact, it's a Greek letter S. And sigma notation, that Greek letter S, actually stands for sum. So since sigma notation stands for sum, it actually is another way of describing series. And this sigma, anytime you see it, we think we're going to add up a bunch of terms. We're going to find a sum. So the way it works is this. The bottom here indicates the starting number. So n equals 1 means we're starting at term number 1 in a sequence. This 5 up here means we're going to end at term number 5, and we're going to add up the terms from 1 to 5. And this formula in here represents our Tn formula. And this Tn formula can be arithmetic, it could be geometric. In this case it's geometric, but it can also be some other formula that generates some other pattern. So this sigma notation is used not just for arithmetic series and geometric series, but for any series. And this is very useful because we are going to end up using this quite a bit once we get into calculus. So we have here, let's see what this looks like. We have the sigma notation means sum. We start at term number 1 and we're going to add up to term number 6. So we have 6 terms to add up. And we can just list this out. Okay? And we can do it the long way if we like. We have 2, we substitute 1 in. So 3 to the power 0, so it becomes 2 plus, because the sigma means it's a sum, we're going to add every term together. We plug in 2, 3 to the power 2 minus 1. It ends up being a times 3 relationship, so we just end up with a geometric series, in fact. But I can just plug in n each time to generate each term of this series. So that's my 4th term, my 5th term, and my 6th term. And then I just take all those terms and I add them all up, and then I end up getting the answer to this series. So getting my calculator out here, 2 plus 6 plus 18 plus 54 plus 162 plus 486 equals, and this equals 728 as the sum. So the sum of the first 6 terms of the term number 1 to 6 is equal to 728. So we could do it term by term, and sometimes we have to do it term by term. But sometimes we can just, in this case of a arithmetic series or a geometric series, we can actually take a shortcut and use a formula if we like. So here is another one. This is we have to check what type of sequence this is. Does it look like it's adding? No, it doesn't look like it's adding or subtracting. Is it multiplying? Well, I can check the multiplying by dividing. So if I divide 1 divided by 4 over 3, my multiplier is times 3 over 4. Dividing those two, yeah, I get a multiplier of 3 over 4. And again, dividing those two, I get a multiplier of 3 over 4. So it looks like this is a geometric series. So that's important to recognize the type of series. And then we can write this in sigma notation and find the sum. So my sigma notation looks like this. This is dot dot dot. So I know I can start at n equals 1. I'm not too sure what to do with that dot dot dot, but I do know how to put this into the Tn formula. And remember that this formula is not for Sn, but for Tn, because this will generate the terms. So my Tn formula is going to be A R, which I figured out, n minus 1, and that's my Tn formula, so that's my sigma notation. Now what's missing is the number of terms, but I have a dot 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 here, so how many terms is that? That really means an infinite number of terms, so I'm going to go, my ending point is infinity. So this is weird because I'm going to have to add up a whole bunch of terms infinitely, forever. I don't know if I can calculate this sum. So right now, I'm just going to put a question mark. We will learn how to do this though, however, because there are some series that add on infinitely that actually have a sum. So we need to study that first. But right now we haven't figured out how to calculate the sum, and many of these sums are incalculable, what we call divergent. This one happens to be calculable in something we're going to call as a convergence series. But for now, we'll have to go back to this problem because we haven't figured out how to do it yet.